This is a demonstration to show how optimizing minds methods and tools help understand what the AI is doing. This is in line with the current push by both the EU and the US, for example DARPA, for explainable AI, and this is especially important for the safety of self-driving cars. This demonstration is on the commonly used MNIST handwritten digit database. However, the same applies to street sign recognition and any other AI application, including deep, convolution, and recurrent networks. What we will do is run a standard SVM method of learning, take the results, convert it to our form, and see what's inside. First, let's look at performance. Here are the results of both the original and our form. The accuracy is the same, and all of the false positives and false negatives for each digit is the same. This indicates that our form behaves just like the original. We can also prove this mathematically. They both get exactly the same performance, but now we want to ask, what is on the inside? What did the SVM learn? To do that, we're going to look at the internal weights of our method. These are the respective optimal patterns that each node of the network has learned in order to recognize each digit and get 91% correct. You'll immediately notice that these patterns do not look anything like the digits that we're familiar with. It learned that specific pixels on the outside of the digits are the most important to perform the recognition, and these pixels are only specific to this dataset. Now let's run individual tests to reveal further intuition. So this is the test image. This is the internal pattern that the network sees. This is the closest of those patterns that it thinks it matches. These are some of the inputs that are pretty well matched, and these are some of the inputs that are not well matched. And these are the activations of all the nodes. So, for example, in this test image of 7, the network decides that this is a 7. And our method is a non-parametric method that works during recognition. So when I hit a button, it's going to load another test image, and you're going to see the activations here change as it's performing its dynamics. And you see here it recognizes this as an 8. Then this is the characteristic pattern of an 8. And we can continue to do this. Here it recognizes a pattern as a 9. If you're not convinced that these are the characteristic patterns, here we present the ideal pattern for node 1, and indeed you see the activation of node 1 becoming 1 and all the other nodes becoming 0. Put in the ideal pattern for node 2, and again you see the activation for node 2 becomes 1 while all the other ones become 0. The key is the basis of the network's decisions is now accessible, and I'm going to use this information to generate adversarial patterns. I've chosen some of the most relevant pixels of these patterns and use those as inputs. When I present those pixels representing 1, node 1 becomes most active by a factor of 10. I do the same for the pattern of 2, and node 2 wins. So it's showing us that, yes, the SVM learns, but it's really learning some sort of statistics unique to this training set, but not unique to digits. This is a big problem of overfitting, and this is why a lot of data is needed for AI learning. It's to try to avoid training that ends up with something like this. Our solution is to do much simpler and faster learning that does not focus on anomalies in the dataset. The SVM took 15 to 20 minutes to learn those weird patterns from the 60,000 training set. We learn from that set almost instantaneously when I press enter. These are the new expected patterns, which also look much more like characteristic digits. When I press enter, it loads in a test pattern of 8, the activations evolve, the network shows what it perceives, and which are the most relevant inputs for this perception. Here you can see a wrong answer, which the other method gets wrong as well, and it's showing you why it's getting it wrong. What is it picking? Here's another one. The key here is that this is much closer to digits. It might not have as high of a performance. The performance is about 80% correct, as opposed to the 91% for the SVM. However, this is much more true to the form. You can tell that the algorithm has learned what are the characteristic and important parts of the pattern. So this is a demonstration of how understanding the internals helps make sure that the network is doing the right thing. A couple of notes. You'll notice the performance at 91.6% max is not the top performance in the field. Both the networks here are a single layer, but this methodology can be applied to each layer in a deeper network. And the second point is that in this form, we can also add a new pattern as we go. For example, I can add a minus. I don't have to retrain the whole network, and I immediately can run the network on all the old patterns and the new pattern. Thank you for listening.